Hello everyone, welcome to the lecture on uncertainty modeling in AI. And today we are going to look at mixture models and the expectation maximization algorithm. In particular, we are going to look at the special case where we are going to solve the probability distribution of P of x, z, conditioned upon theta. And in this particular case that we are looking at would be that x over here would be a set of observed random variables, and z would be a set of latent random variables, and theta would be our unknown parameters. So we are going to look at the case here where we are going to simultaneously infer for the latent random variable as well as to solve for the unknown parameters of the probability distributions given a set of observed random variables. So in comparison to what we have learned in the previous lectures in the first half of the semester, where we saw in lecture 6 is that we are given the full observations. This means that we are given all the observed random variables of x over here, and what we are interested in would be to solve for the unknown parameters that tells us the underlying distribution of this probability functions. And in the first few lectures, we have also looked at the case where we are given a set of query nodes as well as a set of evidence nodes. And given that we know the underlying distribution of the probability of the joint probability distribution, we are interested in inferring the unknown query nodes given the set of evidence nodes. So in that case, let's also write it in the similar form. What we are interested in is this particular distribution over here, that we are given x and z conditioned upon theta. So what we are interested in is that we're interested in solving the set of latent random variables where we are given the observed or the evidence nodes as well as the underlying probability distribution. So in this case here, these are a set of known parameters. We solve for the set of the unknown latent random variables in this joint probability distribution. So today we are going to look at the case that given a set of observed random variables where we are going to solve the latent random variables as well as to solve for the unknown parameters. And of course, I didn't invent any of today's material. A lot of the slides and content of today's lectures, they are taken from especially the first book over here, chapter 8, written by Christopher Bishop, Pattern Recognition and Machine Learning. I strongly encourage every one of you to take a look at this particular chapter of the textbook after today's lecture. It's a very comprehensive write-up of the EM algorithm and the mixture model. And of course, I also refer to some other reference textbooks such as Kevin Murphy, chapter 11, and the unpublished textbook written by Michael Jordan, which you can get from these two links over here, as well as the textbook written by Daphne Koller and Simon Prince. I strongly encourage every one of you to take a look at these references if you are interested. Hopefully, by the end of today's lecture, you will be able to solve the non-probabilistic k-mean algorithm to solve what we call the clustering problem. So just now I mentioned that today's lecture will be revolved around solving this joint probability distribution of x, z conditioned upon theta, where x here is our observed random variable and z here is our latent random variable, as well as a set of unknown parameters that is the underlying probability distribution. And we will see in the first part of the lecture on how this formulated in a deterministic way is equivalent to the k-mean algorithm, and how this is also equivalent to the clustering problem. And we will also see that k-mean algorithm is equivalent to what we call the hard assignment problem. The hard assignment problem, or the hard assignment clustering problem. Then before we look into the expectation maximization algorithm, we'll look at the definition of a Gaussian mixture model, which can help us to formulate the clustering or model the clustering problem. And finally, we'll look at how to solve this particular probabilistic distribution over here, where we infer for both the latent random variable as well as the unknown set of parameters that describe the underlying probability distribution by applying what we call the expectation and maximization algorithm. And we'll see that this is equivalent to what we call the soft assignment problem, or the soft assignment clustering problem. Now, to motivate the clustering problem, suppose that we are given many images of handwritten digits from 0 to 9, as shown in some examples are shown in this particular diagram over here. These are actual digits of handwritten digits collected from the USPS, the American Post Office, in the early 1990s, which is called the MNIST dataset. And this MNIST dataset has become a famous dataset right now, especially in the area of deep learning. But let's use this example to motivate our problem of the expectation maximization algorithm, or the clustering problem. Now, suppose that we are given many of these images, and we can extract, for each one of this image, we can extract a 2D representation. Suppose that this particular image here, we can extract a vector of xn, which is in a two-dimensional space over here. This means that suppose that I can represent this particular digit over here with just two numbers of x and y, for example. And similarly, I can also do this for every one of these digits over here that can be transformed or can be mapped into a 2D representation, or we call this the feature space, the 2D features, a 2D feature space, where we can use this to represent that particular image. And suppose that we can do this for every single digits that we see in the data set, and we get a collection, or we get a set of x1 all the way to xn features that represents, where each one of these represents the every single handwritten digit in the image respectively. And now let us further suppose that we can plot this two-dimensional features for each one of this image out into a 2D plot. Now, suppose that this is how the plot looks like, where we have two axes over here, the x and the y axis, since we are living in a two-dimensional feature space. So what it means is that for each one of these handwritten images, where I can transform it into xn, which is in the 2D space, and now I'm visualizing this in a two-dimensional plot. Now, suppose that this particular digit of 3, which is transformed into the two-dimensional image feature over here, and it's supposed to be lying here, for example. So this is going to be my xn. So I'm going to do this for every single image, for every single feature that is associated with every single image in my data set. And this is most likely what I'm going to visualize after I can plot it out in the two-dimensional space of the features. Now, it's not difficult to observe from this particular plot over here that the features of the same digits, or the same class of the digits, tend to form clusters together. They tend to live very close to each other in the feature space. Now, here in this particular case here, we all together have 10 classes, where the classes are the respective numbers, or the respective digits from 0 all the way to 9. So altogether we have 10 classes. We'll expect that this over here to form 10 clusters, which look something like this, where each one of these clusters actually corresponds to a single class of the digit, because we expect that the same handwriting or the same style of the digits, for example 3, regardless of the variation in the handwritings, we'll see that they are going to form close by neighbors in the feature space once we have mapped them into the two-dimensional feature space with some variation. So we can see that they all don't collapse into a single point over here. For example, this is class equals to 3, for example. So we can see all the digits of 3, they tend to form cluster together, but they don't collapse into one singular point. The reason is because the different handwritings, although it's the same digit, there is a certain variation among them. So we can expect that there is a certain variation that contains this particular distribution here. And since it turns out that the data points with the same digit tend to be associated with the same cluster, this means that all the digits that are close to each other, they tend to form clusters together. They tend to be the nearest neighbor in this feature space. What this means is that it suggests that clusters can be used to represent the complex distribution over the different digits or the different handwritten digits in this MNIST dataset, for example. And now we will face a chicken and egg problem. The first thing is that this is what we are given. If we have all the feature space x1 all the way to xn that are in the two-dimensional space. So this is my feature space. And even though that I know the features in the feature space, the two-dimensional features in the feature space, and it's also important to note that the features need not be just a two-dimension. In a two-dimensional feature space, I give this, or I use this as an example because it's easy to visualize in the on the slide, which is a two-dimensional plane. But this feature can actually go all the way up to m-dimensional space, where there's no limit to m over here. But the limit is just your memory power of the computer. But in this particular case over here, we know that x1 to xn in the feature space, and we also know that these are going to form clusters. That means that the same class are going to cluster together. But the problem is that we do not know the parameters of the clusters. Suppose that I'm going to represent each one of these cluster as a circle, just a circle here, and this means that the unknown parameters would be the centroid of all these clusters, which represents that circle that contains each particular class in this feature space over here. And here we do not know these unknown parameters, so the centroids of these circles, I do not know them, and I also do not know the radius of this circle, for example. So this example over here, it can be seen as the unknown parameters. So this would be the centroid C1 all the way to Cn, as well as R1 all the way to Rn. So these are my unknown parameters that characterize my distributions in this example over here. And we also do not know which data corresponds to which cluster. So it becomes a chicken and egg problem, where if we know either of these parameters over here, the other will become easier to solve. So suppose that I know the unknown parameters, I know where are all the centroids and what are the radius of each one of these circles that I use to characterize the clusters. I would be able to easily associate each one of these features to the nearest centroids in this feature space. And suppose for every one of these features in the feature space, I know which cluster it belongs to, then I will be able to easily compute the centroid by taking the average of all these features that belongs to each respective centroid and computing the variance of it, and to be my radius of the circle that I use to characterize the cluster. But the problem here is that we are facing a chicken and egg problem. This means that we neither know the unknown parameters nor the data association. We do not know which cluster does all the data point belongs to. So we'll first look at the non-probabilistic approach, which we call the k-mean, and the problem it's associated to what we have seen in the motivation example. We can formally formulate it into this particular problem here, that given a data set of x1 all the way to xn of observations, so they're all together n observations here, And suppose that we are already given X in the feature space. So this means that what we are given here is already in the feature space, and the number of clusters has to also be predefined. This means that in this example here, the number of clusters corresponds to the number of classes. The number of classes in the data distribution, and this number of clusters number of classes in the MNIST dataset simply belongs to the number of digits that we are looking at, and in that case we altogether have 10 classes, which corresponds to 0 all the way to 9, which are all our digits. And the problem here is that we want to find the k clusters centers, which we denote as mu1 to mu k. So each one of these mu k is actually in the same dimension space as our data. So suppose that, let me generalize this to m dimension. So each one of these mu would be in the m dimensional space, and where x here also have to be in the n dimensional space. And so this would be an unknown which we want to characterize. And so here we also assume that the cluster is a circle, where we can have the option to estimate also the radius of the circle, but in this case, in the k-mean example, I will show that this is actually not necessary, because we can substitute this parameter with the nearest distance. And the second thing that we wish to find would be the assignment of each point to the cluster center. This is the data association problem. So essentially what we are trying to solve over here is to solve that chicken and egg problem, where we are trying to simultaneously solve for the cluster parameters, the unknown parameters over here, as well as the assignment problem here, the assignment problem over here, where we want to assign each data point to the respective cluster center that we have estimated in the first problem here. And we can also see that just a preview of what's going to come in the later part of the lecture, and to relate to what I have mentioned earlier at the start of the lecture, is that if we denote this assignment as z, our latent random variable z, and the unknown parameter as data, so given all the observations of x, what we are after would be this. We are going to estimate the distribution, the unknown parameter, as well as to estimate the latent random variable given a set of observed variable. But before we go into the probabilistic modeling of this, let's look at the case of a deterministic modeling of this, and we'll solve it using what we call the k-means algorithm. So let me first introduce the definition of 1 of k coding, where for each data point xn, we introduce a corresponding set of binary indicators, which we call rnk, that are either taking a value of either 0 or 1 for all k equals to 1 to k. So k here denotes the number of classes. The number of classes, where let's say k equals to 1. This means that my class of that point, the end point xn, is going to take the class number 1, which means that rnk over here, if it is equals to 1, this means that the nth point is going to take the kth class in my example. And here it's subjected to a constraint where all the summations of the k of all the classes has to be equals to 1. So what this means is that each one of the point can only take one class. So if we were to view this rnk over here, we can visualize it as a matrix. So all the r's, they are going to form a matrix that looks something like this, where the total number of rows that we have are n number of rows. So this is going to be 1 all the way to n. And the number of columns that we have is going to be 1 all the way to k. And this represents the data point, and the column represents the class. So what this means is that for each data point, I'm going to have each entry over here is going to be RNK. For each data point, this means that for each row of this matrix R over here, I'm going to have it sum up to 1, where each entry in this matrix is going to be 0 or 1. And what this implies is that for each row over here, I can only have 1, 1. I can only have 1, 1. And all the rest must be 0. So the intuition behind this is that if I have 1 ones in that particular, in this row, every row of this matrix of R, this means that every data point, for every data point that I have, I can only assign it to one out of the K classes, because there's only one in the whole row. And there is no restriction in the column, because what this means is that for every class that I have, I could have more than one data point that is assigned to that particular class. So in other words, this binary indicator variable describes which of the K clusters the data point is assigned to, and it better be a unique assignment because of this particular one of K constraint over here, that the row has to be summed up to 1. And this is what I meant here. So formally, now we can, with this definition of the one of K coding of RNK, we can formally formulate the goal of K-means into the problem of finding values for RNK and mu K, so that we can minimize the distortion measure, which is a cost function that is defined by this equation over here. J equals to the summation of n. N here is my data point, or simply my observed points, and K here is my class. So what this means is that for every data point, I want to assign it to a closest, or I want to assign it to a centroid, and where each data point, I can only assign it to one centroid over here, as governed by this particular equation, the one of K coding constraint here, where each row of this R has to sum up to 1. And R over here, since it's in the space of 0 and 1. So what this means is that, and since I have this constraint over here, and recall that this R over here, every single row, this is 1 to K, and this is 1 to N. So this means that every single row that I'm looking at here, I'm looking at the n data point, xn over here. So since it has to sum up to 1, this means that only one of the entries over here can be 1, and all the rest has to be 0. And what this implies is that in this cost function over here, it means that when I sum over all the K's, all the class over here, for every data point, when I sum over all the K's over here, only one of this entry here that corresponds to a specific K would be 1, and all the rest would be 0. So I won't take those terms into account, where this guy over here is assigned a 0. I'll only be looking at the term which corresponds to 1 over here, and that corresponds to my assignment. So I have to, my cost here would be the measure of how close this particular xn, suppose that I select mu k as the assignment or the centroid to this particular observed data point of xn over here, where rnk here is going to be 1, and I'm going to use that distance. So this is just a distance measure, since it's x minus mu over here and square. So this is a distance. I want to measure that particular distance. What it means is that now suppose that I have this particular centroid over here, and this is my so this is my mu k, and this is my xn over here. I'm going to measure this distance and put it here. Suppose that I'm assigning xn to mu k from the one of k coding here, and the total, this means that the total sum of this over every single point represents the sum of square errors of the distances of each point that is assigned to its respective vector or the respective centroids of the clusters mu k. And what we want to do here is that we want to minimize this guy over here. So we want to do a argmin of j with respect to r as well as all the mu's, where this r here is our assignment parameter, and mu over here is our unknown parameter. So we want to simultaneously do a minimization over the sum of square distances on the assignment variable as well as the unknown parameters mu and r respectively. Now let's look at the k-mean algorithm. It's a very simple algorithm. So we'll first do an initialization where we'll randomly choose some values for mu k, which is the centroid. So you can imagine that in the 2D space, this is how it's going to look like. Suppose that this is my 2D space. I have all the data points that I observe. So what I'm going to do here is that suppose that there are only two classes, mu, this means that mu1 and mu2 respectively. And what I'm going to do here is that I'm going to simply select 2 points and randomly initialize 2 points as mu1 and mu2 respectively, and then I'll start this k-mean algorithm, which is also known as the Lloyd algorithm, invented by named after this particular guy, Lloyd. And so after I have initialized this mu with some randomly initialized values, we'll proceed on to the first step, which we call the assignment step. This means that since we have the mu's over here from the initialization, for each one of these data point, we would have to assign it to the its respective centroids or its respective cluster, mu1 or mu2, such that it minimizes the cost function, this sum of square distance that we have that we have defined in the previous slide with respect to r and k, which is our assignment, while keeping the mu's over here fixed, the centroids of the clusters here fixed. And we'll see that this is easy to minimize because we are keeping mu fixed and we are only optimizing with respect to the r and k over here, the assignment, and we can while minimizing the sum of square distance. So we can see that it's easy. Intuitively, all you need to do is that for each one of this observation over here, of this observed point xn over here, I just need to find the centroid or assign it to the centroid that is closest to it with a minimal distance to it. And after we have done this assignment step to minimize j with respect to the assignment parameter or the assignment variable, the next thing that we will do would be to do the update step, where we'll again minimize the cost function j with respect to mu now, while keeping rn, the assignment parameters, fixed. We'll see that once you have assigned, so here we can see that it's no longer, because we're alternating between r and keeping mu fixed and optimizing over mu while keeping r fixed. So this will avoid, in other words, this is going to help us to avoid the chicken and egg problem, because we have mentioned that if both of them were to be optimized together, then we will face the chicken and egg problem, which is a hard problem to solve. But in this particular case here, since we are keeping, every time we optimize for one, the other parameter would be kept fixed. And this means that it becomes easier to solve for the problem. So in the update step, we're going to minimize the sum of square distance with respect to mu while keeping r and k fixed from the previous step. The intuition here can be easily seen. Now suppose that after the second step over here, every one of these r is going to get assigned to a certain cluster. In this example, where I only have two clusters, mu1 and mu2, after the second step, each one of these x is going to be assigned to one of the respective two clusters. In the second step, I'll simply use this assignment. I'll simply keep this assignment. Now suppose all these are assigned to mu1, for example. I'm simply going to keep the assignment of r And then I'm going to compute a new mu, a new centroid out of this all this data set. I can easily do this by taking all this data set and computing the centroid, and assign that new centroid to be my new mu. So mu is going to be shifted here, for example, and then this suppose that all these data are assigned to mu2. In the second step, I'm going to use all this to compute the new mu, which is going to be my new mu2. Now let us look at the more formal definition of the assignment step, where the objective here is to minimize the cost function, which we have defined to be j equals to the sum of n, sum of k, rnk, which is our assignment variable, over the sum of square difference of every data point xn and the respective centroid mu k square over here, where we are interested in finding the arcmean of r over j while keeping all the mu k's here fixed. And since we are keeping mu k fixed, what it means here is that we can simply optimize over each one of these Rn separately, which means that recall that particular R matrix that we look at, which is m by k over here, where we say that each one of these row over here, the nth row over here, is corresponding to the assignment of the xn, or the nth point, nth data point in our observation, where it can take one out of the k assignment. And since we are fixing our centroids of mu k over here, this means that we can look at each one of these rows independently, because each one of these data point, they are assumed to be independent of each other. And now in this case here, we can see that since we are optimizing, or we are minimizing with respect to each rnk, the summation over n would fall off from this equation, or this optimization cost function over here, where we will look at only the inner summation over k, and the cost over here would still be the sum of square difference subjected to the 1 of k coding constraint over here. And what's interesting here is that there isn't a need to do any sophisticated optimization over here or differentiation over here. We can immediately by inspection solve for this cost function over here, solve for this minimization over here, where we can see that the minima actually occurs when we assign xn to the current closest cluster centroid, as illustrated from what I have mentioned in the earlier slide. Now suppose that I have a two-dimensional case x and y over here, and I have set mu1 and mu2 to be here, for example. So each one of this r, or each one of this xn, my data point here, in order to minimize this particular distance, since the distance is xm minus mu k square, this means that I'm taking the distance of, I'm computing this distance and computing this distance, for example. So now I can see that d1 and d2 over here, since d1 is bigger than d2, the obvious choice would be to select the, or to assign xn to the closest centroid, such that the distance here is minimized, such that the total distance of each point is minimized over here. And hence we will just simply assign rnk. This means that in this particular matrix we are looking at one particular row right now, since every data point here is independent. We'll look at this and we'll assign 1 to that particular kth class, such that the centroid is closest to that particular xn data point that we're interested in, and all the rest of the entries here will assign it to be 0 over here. Now in the update step, we can also easily optimize it by looking at each one of the centroids separately. This is true because we assume that each one of the data point is independent, and hence the centroids that governs the data point should also be independent. As a result, we will only look at the summation over n in the cost function that we have seen earlier. So j is equals to x summation over n, summation over k, rnk xn minus mu k square over here. And since we assume that each one of this mu k is independent from each other, and we'll just simply do a minimization over each one of the mu k, and this becomes independent of the this means that we can drop this particular summation over k in the cost function over here. So, and one thing to note is that in this particular case, we'll take r and k here as a fixed value. So this would be from the previous assignment step, and this optimization or minimization of this cost function over here can be easily done by differentiating this cost, which we call L, with respect to mu k and equate it to 0, since there's only one variable in this optimization over here. And we can easily see that this gives rise to this equation over here, which we can make mu k the subject over here. And this will give rise to this particular equation, which will allow us to compute mu k. And interestingly, what this means is that we are actually taking the mean or the centroid of all the observation that is assigned to the cluster of k over here. So as I've illustrated in the illustration earlier for the 2D case, suppose that this is xy, and now suppose that all these points here, all these data points here, they are assigned to the k cluster over here. So in the next step here, since we fix the r and k, we fix the assignment over here, we'll simply compute the centroid of this guy over here and call it the new mu k, which is equivalent to what we have seen in, or what we have derived in this particular optimization in the update step over here. Now here is an illustration of how the k-mean algorithm is performing clustering on a two-dimensional example where the feature space is two-dimensional. What this means is that the xn here is going to be in two-dimensional, as well as mu k is also going to be two-dimensional, because this mu is actually representing the cluster center of the in the feature space. And suppose that this is what we have seen, all the xn data point here shown in green over here. So the illustration here is shown in green to illustrate that we do not know the clusters or the cluster assignment, neither do we know the unknown parameter of the clusters, centroids, and we'll first initialize this k clusters centroid. In this case, k equals to 2 because we only have two classes over here. And suppose that we initialize mu1 and mu2 to be here and here. Now the next step here would be to do a minimization over argmin over Rn, and where we have summation over k and then Rnk and the sum of square difference of xn minus ck square here. So in this case here, we saw that in the previous derivation that we can easily do an assignment, or we can easily, for every one of these single data point over here, we will simply assign it to the closest centroid or the closest cluster center. So for example, in this this particular point, we can see that the distance from here to mu1 is actually closest from mu2. So in this case, we'll assign this particular point over here to mu1, which is illustrated in blue over here. And in this point over here, for example, this particular point over here, it's closest to mu2 than mu1. So we assign it to mu2, which we illustrated in red over here. And after this particular assignment step over here, we'll proceed on to do the update step, where we'll assume that the assignment variable Rnk stays fixed, and we'll make use of this to compute the new update of the cluster centers mu1 and mu2. So in this case, we can see that the different colors represents the assignment that is done in the previous iteration or in the previous assignment step, and we'll simply take the centroid, or we'll simply take the average of all these data points and compute the new centroids over here. So this would be our new mu2, and this would be our new mu1 over here. And we will complete one particular iteration of assignment and update. Then as we have done this iteration until it converges, this means that we will know that it converges when there is no change of R and K in the previous iteration. So if I look at the R and K at the time step of t, or the iteration step of t, comparing it to R and K of t plus 1, there's not much difference over here. So this minus this is less than a certain threshold, as well as mu k at t minus mu k at t plus 1. So if this is also lesser than a certain threshold, then I will say that this has already, the algorithm has converged, and I will terminate the k-mean algorithm. So in iteration 2, we will continue to do this assignment and update optimization until this convergence criteria has been fulfilled, and we terminate the algorithm. Now we can see that if we plot out all the cost function, which is the sum of square distances, from the first initialization step all the way until it converges, we can see that this particular cost over here, it gradually decreases and it saturates at a certain after a certain iteration. So this can also be used as our termination criteria, where for each step over here, I'm going to compute my j. So suppose that this is j where t equals to 1, time step equals to 1, and suppose that this is about 1200, for example, and then the next step here, jt equals to 2, and suppose that this is about 400, and the next step, jt equals to 4, and now suppose that this is about 80, and subsequently, as I iterate more and more, I'll see that jt equals to 5. It's also going to be approximately 80. So the difference between the subsequent time step or consecutive time steps of the iteration, if it saturates, then I will terminate the algorithm. I can also use this as a termination criteria for my k-mean algorithm. Now let's look at an example of the k-mean algorithm on the image segmentation, where I want to, for a given image over here, I want to segment it into different clusters based on their RGB information. So every pixel over here, I have a certain value for R, G, and B, and I want to, based on this RGB information, which I take it as my feature space xn is in the RGB space, and then I want to make use of this to segment it or to cluster them together, where similar pixels with similar RGB values would be clustered into the same class. Now, in this example over here, suppose that I have k equals to 2. This means that given this particular original image, I want to cluster it, or I want to segment every pixel belonging to k equals to 1 or k equals to 2 class. This means that all the similar colors, they should be grouped together into one particular class, and those that are different would be belonging to the other class. So in the case where I perform k-mean on this RGB value, which I take it as my observation, now this is the result that I will see. I can see that most of the colors of yellowish, or that's close to yellowish or orange, it will be cluster into the same cluster over here, and those that are close to blue, we can see that they are going to be segmented into another cluster in this result over here. Now suppose that k equals to 3, we can see that the darker shades are now my third cluster over here, and by performing k-mean, this is the result that I will get. Here's another example where, given this original image, if I were to do k equals to 2, this means that every pixel, I want to group them into two classes where the more similar RGB values, they are going to cluster together, and this is the output that I will get for k equals to 2, where I can see that the darker shades, they are all going to be clustered together here. So these are the darker color, the darker shades, they are all going to be clustered together. And the lighter colors, they are all going to be classified, or they are all going to be clustered together here.